Welcome, everybody. Today's webinar is The Doctor is In, Quick First Aid for Broken ClickHouse Clusters. My name is Robert Hodges, and I'll be presenting today with Diego Nieto. We'll do intros in just a second. We also want to give a huge shout out up front to Tatiana Saltikova, who helped prepare many of the materials that are used in our presentation today. Speaking of the presentation, here are a few tips which will help you enjoy it more. First of all, this presentation, as you probably just heard, is being recorded. You will get a link to the recording as well as a link to the slides shortly after the webinar ends. It usually comes out the same day at latest the next morning. We also have time for question and answer. So if you have questions about these topics or about other ways that ClickHouse servers can break, feel free to put them either into the webinar chat or the Zoom Q&A box. You should find them on the little menu bar. What we'll do is we'll take the questions at the end of each section. We're going to talk about 6 important types of problems that you can have with ClickHouse clusters. We should also have some Q&A time at the end. I think that clears out the housekeeping items. Let's dive in. But first, we need to deliver a very, very important warning. If you or a loved one is experiencing a data-threatening ClickHouse emergency, please stop listening to this webinar right now and get help immediately. If you want to get it from us, here's a couple of links. You can talk to us on Slack. That's where Diego and I usually hang out, along with a lot of other Altinity people. You can also hit the contact link, set up a meeting to talk about what you're working on, or you can go to the ClickHouse Slack. Go get help. Don't wait for, don't wait till it's too late. With that, let's go back to the presentation and do some intros here. So once again, my name is Robert Hodges. I am the CEO of Altinity. I've been working on databases actually for about 40 years, so it is 30 plus, but really a lot longer. I've been working a great deal on Kubernetes and data since 2018, and I've been working with ClickHouse itself since 2019. So I also have with me Diego Nieto. Diego, you want to just introduce your background a little bit?
Yeah, hello. Nice to be here, Robert. Thanks. Yeah, I'm Diego. I'm support software engineer on Altinity. Yeah, and I'm mostly interested in databases, ClickHouse, obviously, and others like Postgre, and also Python and Rust a little bit.
Great. And just a little bit about Altinity. So we do support and cloud services for ClickHouse. Altinity.cloud is our cloud platform, which allows you to run ClickHouse either in our cloud, in the case that you just want to have an endpoint and get started, or we can also run it in your own cloud accounts using a bring your own cloud model. We are, as some of you probably already know, we're the author of the Altinity Kubernetes operator for ClickHouse. It's an incredibly popular, one of the most popular operators on GitHub for databases. We also are the authors, or the maintainers, I should say, of ClickHouse Backup, Altinity Stable Builds, and a number of other open source projects. On top of that, we've contributed on the order of 600 PRs directly to ClickHouse itself. So we're very active in contributing to the project as well as interesting and useful ecosystem projects. So enough advertising about us. Let's just jump in and introduce ClickHouse for those of you who are not familiar with it. So ClickHouse is a real-time analytic database. You can think of it as kind of uh, sort of combining the best aspects of a transactional database like MySQL or an analytic database like Vertica, for those of you who've been around, the very popular database a few years back. So from the MySQL side, you have the fact that we can understand SQL, everything's organized in tables, runs practically anywhere, is open source, and simple to set up and use. From the analytics side of the house, we have a shared nothing architecture. That was the initial architecture that ClickHouse was developed with, where you have a bunch of processes on a network. They each have storage. They communicate over the network to get queries executed. ClickHouse, of course, is evolving to a more modern architecture, which uses object storage as a backing store. Like just about every other analytic database on the planet, it stores data in columns. Those columns are highly compressed and and include extras, which we'll talk about, like secondary indexes, primary key index, things that allow you to find things and pick them out quickly in queries. Speaking of queries, ClickHouse has very efficient vectorized execution. In other words, treating the columns as arrays, pieces of which can then be grabbed, pushed onto and processed on individual cores within a CPU. ClickHouse is super good at soaking up all the available cores that you have. In addition, it can blast the queries out in parallel across many nodes on the network. And ClickHouse is very scalable. So it's common now to have systems that process more than a petabyte of compressed data. And in fact, as time goes on, we're seeing even larger uh, storage as well. So all these things taken together with the open source licensing, ClickHouse's Apache 2.0, very large community, it's made it hugely popular as an analytic database. It's probably the single most popular real-time analytic database on ClickHouse, if not the most on GitHub, if not the most popular database overall. So let's get to the matter at hand. What we're now going to talk about is problems that you can have when you are running ClickHouse in production. And the problems that we're going to talk about today are interesting because they are things that if you're just running ClickHouse on your laptop, you're very unlikely to see. In fact, they're kind of hard in some cases to recreate in a test environment. They are problems, though, that appear on large systems that have a lot of data, maybe heavily loaded, maybe under-resourced, uh, maybe hitting peaks in processing, things like that. And so what we're going to do is dive in and talk about six of these problems, how you recognize them, what's actually going on, and how you fix them. So let's jump in. So one of the most common problems that people hit in production ClickHouse systems is what's called a too many queries error. Let me show you an example of it. So if you have a busy ClickHouse system and, for example, you have a lot of different users or you have a lot of different applications that are accessing that system, you may from time to time see an error like the following. And what it says is too many simultaneous queries, maximum 25. In this case, just to be clear, I've set the limit down to a very low level so that I could simulate it. But what this happens is your query doesn't run. It just breaks and you have to retry it later. So this is a surprisingly common error in busy systems. Let's go ahead and have a look at what's actually going on here. So first of all, when people see this, their immediate response is, hey, I got to fix this. And there's a number of options for fixing a too many queries error. And here's four of them listed, probably the most common ones. They range from making your queries more efficient all the way to increasing a limit called max concurrent queries. And that's actually the limit that we're exceeding when we get that error message. So which of these should you use? Well, if you just talk to your manager, he or she will probably say, well, just raise that limit so that we can process more queries. It turns out, though, that as we look at fixes for this problem, that's possibly the worst way to fix it. In some cases, the limit is truly too low. I've set this artificially low, but in most production systems, it's set at a reasonable level. And what it's really doing is protecting you from having your ClickHouse server being swamped by a very large number of users, in which case the queries will just go slower and slower and slower until the system just grinds to a halt. There are other options, though. So really the best case when you see this, if you have the time, is just to make the queries more efficient. Because what's really happening here, the reason that the queries are piling up is because they're taking a while to run. So if your queries run faster, then you're less likely to hit this limit. And in fact, if your queries run very fast indeed, uh, you won't see this problem at all because the number of concurrent queries will just never reach such a high level. So making the queries more efficient is the first thing that you should, or the first thing you should think of when you see this error. The second thing, if you can't do, because sometimes it takes a while to fix queries and get them deployed, the second thing, and the quick fix for when this happens on Sunday morning, is just to add more resources. So if you're operating in the cloud, uh, or you're operating on Kubernetes, it's usually pretty simple to just scale up to a different to a larger VM size. And by adding more CPU, adding more memory, particularly CPU, you can basically make this problem disappear. The third thing, which is kind of a middle ground, is sometimes you have particular applications or users who are just beating up the system. So one of the things you can do is put limits on those particular users so that so that they will see queries break, but they won't break everybody else's. And that's kind of a middle ground where if you can't fix something and you can't get somebody else to fix their stuff, you can at least protect other users from the problem. The final thing is when you've looked at all these, go ahead and increase max concurrent queries, and we'll show you how to do that safely. Let's dive in and look at specifics on these. So here's a really simple example of fixing a query. Uh, Basically, just think of a way to do it more efficiently. And ClickHouse almost always, any given query on ClickHouse, it's almost always possible to make it faster. This is a really trivial example. I'm computing the average of a series of numbers that range from 1 to, I believe that's, looks like a billion there. Uh, and so, of course, I'm having to scan the numbers, add them all up, and then divide by the number of numbers. Well, of course, I could just take a step back, and if I really want to calculate the average for that series, I could just do it analytically with this closed expression, uh, a billion minus one divided by two, that gets me my average. This is, of course, a silly example, but it does illustrate the fact that by thinking about a query differently, it'll run much faster. Let's look at limiting users. So here, one of the most useful features that you can use is to have a settings profile. So a settings profile allows you to set limits that apply particularly to a given to a given user or set of users. And this is an example of the RBAC command that you can use to do that. So we're setting these two limits, max concurrent queries for users. So any given user can only have 15 concurrent queries, and there's a limit for all users under this profile, uh, which is going to be 20. In the test system that I was playing around with, I had set the limit at 25. So this should protect us from these users. And then when you do a create user command, here's how you assign here's how you assign that settings profile. Let's look, of course, at max concurrent queries. So there are times when when raising this is absolutely the right thing to do. I said before, it shouldn't be the first thing it shouldn't be the first tool that you pick up, but there are times when you truly have a limit that's set too low. You've added resources, uh, or you've got plenty of resources. So what you want to do in this case is have a look at the server and say, hey, is this thing overloaded? A really common thing to look at is load average. So if you can see that the load average is not particularly high, you can see that you're not, use something like htop, you can see that you're not saturating the CPUs, any other metrics that you can think. This it's then time to think about raising this level. So if you see you have adequate resources at that point, you could go ahead and raise max concurrent queries. I'll show you how to set that in just a second. But if you see you don't have enough resources, then your next step is to go ahead and increase server resources and run the check again. So the thing we do when this comes up on Sunday morning, as I mentioned, is the first thing we do is tell people, hey, just add more resources. And then on Monday, we can go ahead and figure out what's really going on and get you a long-term solution. So this is the process you follow, and then you can do this safely uh, and not bog your system down. Because if you don't do this check and you just raise max concurrent queries, say it's at 100 and you raise it to 500, what will happen is you'll simply pile up with 500 queries instead of 100, and the system will jam to a halt again. So speaking of making this update, uh, here's a quick reminder. This is max concurrent queries is a setting. It's a global setting for the server. You can set that. Using XML, and you just make a little max connections.xml file, and you stick it in the config.d directory as is shown here. When you make this change, ClickHouse will pick it up without a restart, which is nice. Okay, so I think at that point, that is going to be it for the too many queries errors, but I do see a couple of questions here. Diego, you want to jump in and answer those?
Yeah,
So
yeah. Yeah, about these restrictions that Robert was talking, yeah, I mean, they restrict ClickHouse users, not operating system users or host level, because I mean, the queries will be executed by a user which has a profile, and I mean, there's no connection between operating system user and ClickHouse users. They are totally different. It's like any database. They have its own
exactly.
set of uses. Yeah.
Yeah, and so there are things that you can do that at the operating system level, but they're mostly get me more resources. Give me more. I'm running out of my queries are running too slow. That's causing me to hit this limit. So go ahead and spin up a bigger VM, like double the size of the VM or quadruple the size of the VM. And since there's more CPU, we'll be able to have more throughput. Great. Thanks, Diego. All right, with that, let's go to the next problem. And that is too many parts. And this, I think, just about every person who uses ClickHouse, at least if they have a moderately large system with real data on it, has seen this error. Let's dig in and see what it looks like. So before we do that, I'd like to explain a little bit about what parts actually are, because they're a really critical part of ClickHouse tables, and it's important to understand what they are and why they are there. So in large databases, particularly analytic databases, we partition the data, which is to say that we divide the table into pieces that can be created that can be treated as essentially independent parts for the purpose of query as well as managing the data. For example, if you have time series data, perhaps from from observability systems, it'll have a timestamp. And what you might do is you might partition the data uh, to group all the data from a single month in a single partition. And then within that partition, you will further split up the data, or ClickHouse will do it for you, I should say, into parts. And these are just chunks of the table that where everything in that chunk is within a single partition. And then ClickHouse treats this as sort of the basic unit of read and write when it's inserting data as well as when it's doing updates. So this is an example of what the parts look like. You can see that first part is or first bit of the name, 2019-01. That's actually the name of the partition. So this is January 2019, and we see three parts. And then this table shows you a little bit about what's inside them. Um, Another thing that's really important about parts is that ClickHouse manages them in the background to try and make them as large as possible. And in fact, this is the origin of at least largely the origin of the word merge tree, which is the name of the table type, because what it does is it merges data over time. So when you insert a chunk of data, what ClickHouse will do is by default, it will create a part of up to 1 million rows, and it'll just insert it into the server. Now you can immediately query that part, and this is very advantageous because as soon as the insert responds back to say, "Hey, it's successful," you can immediately run a query. But what will happen is if you allowed those parts, which are often, say 10,000 or 50,000 or 500,000 rows, those are too small for efficient queries. So what ClickHouse is going to do is it's going to watch the parts as they're arriving, and then it's going to systematically rewrite them into bigger parts. And what this then means is that you have longer run lengths, you don't have to open as many files. There's just a bunch of other advantages to uh, to this process, and it is key to enabling high performance. Operations like updating and deleting a table will also rewrite these parts. So that's what's going on with parts. And so when we see this message, uh, which is too many parts, typically what will happen is you'll see something like the following, where it just says too many parts, and then it has this kind of mysterious message that says merges are proceeding significantly slower than inserts. And this is the thing that usually grabs people's attention. In this particular case, that's not really what's happening. What is actually happening is we're hitting a limit inside ClickHouse that says, hey, this is the maximum number of parts that we allow within a partition. And if we get more, we start rejecting, or there's another setting that allows us to delay the inserts so that ClickHouse doesn't get overwhelmed. And let's have a look at this setting. So it's called parts to throw insert. And this is a merge tree setting. It can be set globally. You can set it on the table as part of a settings, uh, a clause that's at the end of your table definition. You can set it on queries. You can also put it in user profiles. So what this does is gives ClickHouse the ability to limit the number of parts so that per partition, because what we don't want to do is overwhelm that merge process and have it just get completely bogged down with merging parts. That's another way that you can you can bog down a ClickHouse server. So when we see this error, what we're really hitting is this limit, and then the question is, what can we do to fix this problem? So there's a bunch of root causes. The simplest one, and the one that we see most often, is people simply have inserts that are too small. So analytic databases use column storage, which is very efficient for reading, but it's not very efficient for writing. And the reason for that is by default, ClickHouse is going to create a couple of files for every column. So that means that if you have a table with, say, 100 columns, in order to add a row of data, you would actually have to go and create 200 files. So what we really want to do then is and this would be very slow. We want to have larger batches. So when you see this error, the first thing you want to think about is, hey, are my batches too small? And this is an error that practically everybody who first uses an analytic database is likely to make, is just trying to, for example, insert things a row at a time. So make your batches bigger. What's big? Well, a million rows is great. Uh, 10 million rows is also pretty good too. ClickHouse can take very, very large batches, so don't worry about that. Sometimes it's a simple change in your app to do this. Another thing you can do is enable what are called async inserts. So this is just a setting, and what ClickHouse will do is it will automatically buffer the inserts in memory and until it hits a limit, and then it will push them into ClickHouse, creating bigger parts. Downside, you could lose data if ClickHouse crashed while these things are buffered. Another way to do this is that's more outside is instead of having your applications write directly to ClickHouse, have them write to Kafka and then read the events from a Kafka topic. What that does is basically it allows you to then choose the amount of data that you want to read from your upstream sources. So these are three good ways to make your inserts bigger. The second thing is to look for just issues with the way that you are generating the inserts. And one thing that people don't always realize is when you're inserting data in general, you want to try and make it go to one part or one partition. Uh, so for example, if you're loading data by time, uh, it's great if everything can have pretty much the same it can have pretty much the same date. And the reason for that, or be within the same month or whatever you're partitioning by. The thing is that if there's a mismatch between the inserts, what can happen is the insert may come in and it may be 100,000 rows, which is a good size of insert. But if it doesn't match the partition key, more or less, you could actually spray this out over a bunch of partitions and, for example, create, say, like 100 partition or like 100 different parts because they're going to be created in each of the partitions. This is going to create a lot of parts. Uh, and that's another way that you can hit this error. Third thing, materialized views. This is a subtle one, and materialized views will read the data. It's basically a trigger that operates on the arriving data. It will run a query and then it'll put the results of that query in another table. Again, if that table is partitioned radically differently from from the table that you're reading from, you can get a case where the materialized view will be quietly generating hundreds or even thousands of little teeny parts and will again block your system. This is a, a case I actually saw in a production problem a few months ago that took a little while to figure out. And then finally, there are cases where ClickHouse is simply not optimized and it's just not merging fast enough. In this case, there are some advanced settings. For example, there's a setting called max bytes. I'm not going to read the whole thing, but it basically tells ClickHouse to preferentially merge smaller parts first to keep them from building up and getting large numbers. At this point, though, if you're going to use this, you need to start reading the code. These operations are not terrifically well documented, so you want to go into C++, and there's usually a comment that explains what they do. So these are important ways to fix too many parts errors. Uh, let's turn to see if we have any questions. So Diego, do we have any questions piled up on this one?
Nope, no questions.
Okay, great. Well, folks, if you have questions, feel free to queue them up. We can also, if something occurs to you, we can get to them by the end of the talk. Let's go now to our next problem. Detached and broken parts. So speaking of parts, let's consider sort of bad things that can happen to them. In addition to have too many parts is a bad thing happening to you, uh, but there's things that can happen to these parts once they're inside ClickHouse itself, and that can lead to either detached and or broken parts. So what kind of bad things can happen? Well, let's look at a simple view of a cluster where we have replication between three ClickHouse nodes, and we have a part that's living happily on one of these nodes. In fact, if it's replicated, that exact part, you would expect to see it on all three replicas, but I just drew it on one for clarity. So what can happen to it? Well, a bunch of things. Uh, it is not uncommon for parts to get detached by humans for some reason or another. They may be you may be moving them, for example, or you may decide that, hey, I don't need that part, or there's various reasons why they could be removed. Um, Another thing is you could have a part which is just left over from a merge operation where the because what happens is ClickHouse, when it merges parts, it will pick a series or a sequence of parts to merge into a single larger parts. And then normally what it does, it throws away the old parts when it's done. From time to time, this doesn't happen, and you'll get a part which is just lying around, um, and the data is already there, and it's just sitting there detached, so you don't really need it. More serious problems are that you may have a part that, due to a bug or due to load on the system or something, is simply something that is out of date that was never dropped. Um, it may or may not be covered, but this is uh, by other parts, or it might not be recorded in Keeper. So for various reasons, parts can be added into a server, and then we fail to correctly notify Keeper, or Keeper itself, the metadata got damaged. In that case, we're going to have to figure out how to get that information back in. And then the final problem, of course, is that parts sooner or later get corrupted. So you can have a bit flip in some, like in a file like checksums.txt, which is inside the part. At that point, ClickHouse can no longer read the part. And in this case, you're going to have to do something to get another copy of it. So let's uh, let's dig into this a little further. So the first thing is that if you have parts that are having problems, they usually end up in detached parts. So ClickHouse, for example, will let you detach parts yourself, but if it detects on startup that a part is broken, for example, the checksums don't match, it's going to detach it for you. And this is an example of where we find that data. We can see that for ourselves. We can select from system.detach parts. And this query shows us that we have one part, the first one, which was actually just detached by a user. I happen to know because I did it myself. And then another one, which was actually broken on start. And what happened there was there was a file corrupted in the part. You can actually simulate this yourself by going out to storage and deleting a file and restarting your server, and you'll see this message. So that's a real broken part. And that might be something we want to do something about. So as you investigate these parts, there are ways that you can find out for a particular type of a broken part. You have this thing called the reason, and that gives you kind of a clue of what ClickHouse thinks is wrong with the part. And then you can go and compare it, for example, with system.parts, and that is the list of your live parts that are healthy and attached. And in this particular case, I ran a couple queries and I'm able to see that, hey, this broken on start part is actually that same part. So it gets renamed when it gets on the restart. You can see the same name down in a live part. And in fact, that's exactly the same part. What happened here? This was a replicated system, and what ClickHouse did was when it detected that that part was broken, it automatically fetched the same part from another replica, so the problem just cured itself. In this particular case, this is a covered part. Even though it's broken, we can go ahead and delete it. So that gets us to the question of how do we fix parts? Um, and here's a non-exhaustive list. This is one of the hardest places to give general guidance because there's so many ways that parts can get broken or detached that it's hard to give you clear guidance that covers every single case. But here's some of the big ones. Uh, so if there's no reason, there's a pretty good chance that it was just attached by a human for some good reason. And so the first thing you should do is find out, uh, was it a good reason? And if the part wasn't supposed to be detached, just go ahead and attach it again. Alter table attach part. We'll just put it back. It's an almost instantaneous operation. Um, the other two uh, another reason which comes up, which is um, excuse me, it comes up and it has a couple different names. Is it could either be marked as ignored or covered by broken. What that generally means is it's a part that is already the ClickHouse can detect that it already has the real part in the table. In this case, you can just go ahead and find all the parts with those reasons and go ahead and drop them and use the alter table drop detached part. Similarly, cloned. Uh, that's a part left over from fixing a lost replica. We'll talk about lost replicas later, but that's a replica that's basically gotten detached from its metadata in Keeper. Again, if you see those, you can just go ahead and drop them. The ClickHouse doesn't wipe them out automatically because it wants to give you a chance to check, but the cleanup is simple. So broken on start or broken, that's a corrupt part. And generally speaking, there's a case where it's safe to delete. That's where if it's covered by another part, you can go ahead and delete them. And the query to do this, to generate the commands for this is fairly long, so I have a link to it here. You run that. If it's not covered, then you have a problem. You've really got lost data here, and you may want to have a close look to see what's going to see if it's something you value. And then finally, parts could be unexpected. And what this means is, hey, we see a part in the table, or ClickHouse found a part in the table that it can't see in Zookeeper. And so ClickHouse is then asking, why is that? We're going to detach the part because we don't think it belongs to the table. Other people don't have it. And then it's up to you to figure out what's going on. If you think it's a part you actually need, you're going to have to run a procedure called restore replica. And we're going to talk about that in the context of another problem, which is fixing lost replicas. So these are the main types of problems with detached parts. Let's talk about one variation on, and that is suspicious parts. Probably some of you who have run ClickHouse at scale have seen this problem. It typically happens on startup. So what ClickHouse does is on startup, ClickHouse is going to check the parts. And because it goes through a process of finding the SQL metadata definition for the table and attaching it. And then it examines the parts to make sure that they're healthy. And what will happen is if ClickHouse sees more than a certain number of what appear to be broken parts, it will just stop. And and the reason that it does this is important because ClickHouse is basically protecting you from a case where you change the configuration of ClickHouse. Let's say that you for example change uh, the link or the address of a part of a replicated uh, table in Zookeeper, so you're actually pointing to the wrong location. Or let's say that you did something, you move storage around and the configuration is now messed up. ClickHouse is basically giving you a chance to look at it and 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 fix it because it could be a configuration problem rather than just plowing ahead and detaching all the parts and restarting. So the first thing you want to do when you see this problem is actually check to make sure your configuration is okay. If you haven't changed it recently, you're probably fine. But in which case, you can now, there's a variety of ways that you can get past this. You can go ahead, there's a merge tree setting called max suspicious broken parts, you can just make it a big number. And that will let ClickHouse come up. You'll end up with a bunch of detached parts, but at least you can, your system will come up and then you can start to do, to start poke around and and fix it. Another thing you can do is if you can get on the host, you can actually edit the SQL file, which contains the attached table command, and you can add that as a setting, and then that will let that table come up. That's good because then ClickHouse will still protect you if other tables have the problems. And then finally, again, if you can access the file system and you know that things are safe, you can just do a force restore data where ClickHouse will go fetch data from other replicas, and it will uh, it'll bring the system up. So that's how to fix this problem. Long range, when you start to see a lot of broken parts, it's usually a problem with the way you're running ClickHouse. So these problems are pretty rare if your system is properly tuned. In fact, if you're running on a desktop or just sort of doing development type activities, it's usually pretty hard to create to break parts or to cause them to detach. So these are this, if you're seeing this problem, particularly if it recurs, here are some things you should really look at. First, scale up your hosts. Uh, so because one of the ways that you can get detached parts is that uh, ClickHouse is crashing in the middle of operations, in which case you can get partially written data in a part, other kinds of problems. You can also, this is also a really good time to, a really good way to trigger bugs in ClickHouse is just to have it crash a lot. So adding hosts or making your host bigger is one way to address that. Another thing, once again, is load the system less, by making your queries more efficient. A third thing and a fourth thing are really important. Don't overuse replication. So it's possible to, think about, hey, what's the ClickHouse works best if you have a few really big tables and a lot of lookups. Um, so, but if you have like hundreds of replicated tables, this is going to create situations where replication could get bogged down. Uh, there's now going to be differences between hosts if things crash and restart. That, that and changing data can create conditions where, again, ClickHouse will either write things incorrectly or get caught in the middle of a write, and cause the parts to become inconsistent, and that just leads to problems. So these are all things that you can do long term, which will help make your system more efficient. So that's it for broken parts. Sounds like Diego, looks like you had a question on broken parts. Or did
Yeah.
you have something?
Yeah, yeah. One. It's interesting. I mean, it's like, what do you consider if dropping a part is like losing or data loss? I mean, I think you were referring to detached broken parts. But let's elaborate. If you drop manually a part because you did like alter table drop part, and because oh my God, I just made a mistake. Then you have like 8 minutes to undrop it, and there are new commands in newer ClickHouse versions where you can undrop a part or a table. And for the broken parts, as Robert said, there may be data loss. Yes, if the part is broken, and imagine that some of the columns in that part are corrupted, you may recover the rest of the columns from that part. But those columns that were corrupted, you could not recover. So the data loss will be partial.
Yep. Great. Thank you very much. So this is definitely, there are cases where you can really lose data here. And again, when you get into those, that's a data threatening emergency. Sometimes it's a good idea to start reading the code or get help. We've got three more problems to go. I'm going to speed it up a little bit so that we get done on time. Uh, let's talk about stuck mutations. This is a popular problem, and let's first of all look into what it is. So first question that you get, and this is everybody who's new to ClickHouse, ask this: what are these things called mutations? Well, a mutation just means that you have asked ClickHouse to change a table. And they come in different varieties. which are range from relatively expensive to relatively lightweight. Uh, a very common and probably the most heavyweight example of a mutation is to alter table delete, where you're actually removing rows. And this is heavyweight because we actually have to rewrite every part where we're removing rows. The part has to be completely written and replaced. So very heavyweight. Or you could be adding a projection or dropping a projection. In this case, you're either adding or dropping files. There's no rewriting necessary, and it's only it only affects a small amount of the part, and the rest of the stuff can just be carried over. Similarly, doing things that modify a single column, very common operation to change the data type or add a new column. These only affect that column, but do not affect the rest. So in all cases, ClickHouse will process these in a queue and create new parts. So here's how they're applied, and I won't go through this whole picture, but the basic idea is that when you do an alter table, it's going to stick it into a queue, which you can look at, and we'll show an example of this in a second. Um, and then if you didn't ask it to wait around, there's a sync option. The alter will just enqueue it, and it happens in the background. Otherwise, the alter will wait until it's finished. And ClickHouse in the background will then go ahead and it has some threads that are looking for parts that need to be rewritten, and they will in due time process these writes, and eventually your mutation will be done. So there are three ways that these can get stuck, and your mutations are logged in the system.mutations table. This is a place you want to know about if you're doing this. And here's three ways they can get stuck. First, you can write a bad mutation. So there are some mutations that ClickHouse will happily queue them up, but it can't tell they're going to fail. In this case, we're trying to do a conversion of a string value to int, and some of the values fail. If you are trying to mutate that table and you have that in front of it, another thing that can happen is that you've got another mutation which is waiting on that mutation to finish. But and in fact, this is a mutation that was trying to fix that problem, but because it's second in the queue, it will never run. It's blocked forever until this first one gets deleted. And then finally, and this is the most common problem that people hit, if you do mutations on large tables, they're slow, particularly one where you're deleting rows and you end up having to. That's probably the best. I should have used a delete example. Uh, that you're going to have to touch uh, the entire part, and if you have, say, thousands of parts and they're very large, then this is going to take a long time. So these are three basic ways that you can get stuck. Um, you can find out what's going on with your mutation, and these are tables that you really want to get you want to get familiar with. System.merges shows you actual merges that are happening on parts. System.mutations shows you the queue, so you can see the queue and the order that they're processing in. And then here's a handy command down at the bottom to just to look for uh, mutations that have had at least one error. So because it logs the time that it failed, and it also gives you the error message. So these are things that you want to that you want to look at if your mutations are slow. What do you do if you got a stuck mutation? Well, there's kind of two ways to deal with it. The first is kill it. So if you have something that you've accidentally kicked off a huge mutation, or it's a mutation that's just broken, like that first example, kill it. And so the kill mutation command, it's kind of like killing a query. You just uh, give matching column values, and it will zap that in the table, and the mutation is gone. Unless you hit a bug. There are cases rarely where the mutation won't stop, in which case that may be a problem. But generally speaking, that will unblock the queue and other things can run. The other answer, just wait. If you have a big table and you did mean to do that mutation, you're going to have to wait. It's going to be slow. So just take your time, take a nap, do something else for a while, and after a while it will complete. So with that, do you have any questions, Diego, in the list on related to mutations, or shall we continue?
Nope, no questions about mutations.
Okay, great. Let's look at stuck replications. So mutations were stuck in a related story. You can have stuck mutations, and sometimes these can lead to stuck replication, but there are other ways that replication can get stuck as well. So let's dig in and find out about this problem. So first of all, let's talk a little bit about how replication works. So when you insert a part into a replica, what it does is it installs that it it creates the part, writes it out to storage, and you get a copy, for example, on the left side, and it also updates the metadata in Zookeeper. Other ClickHouse servers that are replicating that table will watch that metadata. When they see a new part arrive, they will go grab it and apply it. So there's basically a queue of things that are waiting to be replicated, and it looks like the following. So as the parts are being added to each of the replicas, what will happen is you'll see that, and these are records that you can see yourself in the replication queue, is for example, you might add the right side replica might add uh, uh, items 1, 2, 3, 4, where we're basically adding 3 parts. They get added to the server. So these are things that all the other replicas should go grab. And then there's also an operation to merge them because ClickHouse looks at those parts and says, hey, these are too small. I'd like to merge them to collapse them down to something more efficient. And so that gets replicated as well. And so you have this queue, and it's basically what ClickHouse does is it uses Keeper to hold this queue and to ensure that the queue is properly synchronized and things don't happen out of order in a way that would corrupt data. So you can actually, so if, and normally this works fine. If on lightly loaded systems, you're rarely going to see problems. But if you do think that replication is broken, there's a number of things you can do. First of all, just check the health of your replicas. So this is an example where the first thing you can do is use system.replicas. It has a bunch of columns, and it basically, there's a line in there for every column or for every table that is using a replicated merge tree. You can find out what the state of that table is. You can also run that query over the entire cluster to see if different tables in different locations are in different states. So that's uh, and for example, one of the things you might look for, a very important one is read only, which means for some reason this replica is not able to accept changes because it can't properly. We'll talk about it in a minute, but typically because it can't talk to Zookeeper. Speaking of Zookeeper, you can check to see whether it's working. So there's a very handy table called system.zookeeper connection. If ClickHouse can't talk to Zookeeper, it won't be able to replicate things. You can run this query and it will tell you what your Zookeeper is up to. Um, if you need to dig more deeply into Zookeeper because you think maybe the metadata is screwed up, you can actually, from the system.replicas table, you can get the Zookeeper path where the replica metadata is stored. You can take that path, you can select for it in system.zookeeper, and you can actually see the contents of the nodes. I just did a count here, but you can actually see the detailed metadata if you're interested. And then finally, you can check the state of the replication queue itself. This is a very simple query. The replication queue is quite rich in data. This reference down below from the Altinity knowledge base will give you lots of ideas about how to fix it. But this is a very simple query that says, hey, how many entries do I have in the queue and how many of them have had errors? And what this says is I've got a blocked queue. I've got 6 entries. It's blocked because they're actually failing. So that gives you a sense of how you can look at things. What are the problems that look at the state of replication? Here are some common problems and how to fix them. Uh, Replicas are read only. So most common reason is they can't see Zookeeper for some reason, or uh, or Zookeeper is unhealthy. It could also be that the replica is just gotten so out of sync with Zookeeper that it can't replicate anymore. Another thing is a replication queue could be blocked by mutations. This is probably one of the single most common reasons that replication is blocked. Uh, look for if you have large mutations, this is a reason why large mutations are not good because they will block replication, or they can. In that case, you either wait or kill them and run them later. The other thing is you may have broken mutations, as we showed before. So delete them, get them out of the way, and free up and let replication clean up. For a variety of reasons, sometimes old replication tasks can just hang around. Uh, in that particular case, you can go and look at them. You can actually delete them out of the queue. These are some conditions where, for example, old tasks that are 24 hours old. If they didn't complete in 24 hours, they're probably never going to complete. So mutate parts and merge parts tasks can be safely deleted. And then a final one, and this is very common if you're, for example, just under resourcing ClickHouse, replication may just be overloaded. Uh, Replication does require reading and writing, and and so if you don't have sufficient resources, you have very high query load. Uh, Sometimes just adding resources will cure the problems. And a final thing, speaking of curing problems, is a lot of replication problems. If you just wait, they will get better because say you have a large mutation passing through, or you have a big batch job that's just loaded a bunch of data. Sometimes it just takes a while for it to go through. Your system will lag for a while, but wait for an hour and it may cure itself. So don't panic when you see this problem. Uh, it can often be, it will often fix itself. So with that, I think that's the. Do we have any questions about? Uh, Diego, do you have any questions about replication that we should address here that will add to the discussion?
Yeah, one about replication and one about mutations. I just answered the mutation one, but it's quite interesting, so I will elaborate if you don't mind. While mutation is running, what happened to reads? That reads get slowed down or block? Well, short answer is no, but when you issue a mutation, I mean, when it's scheduled, ClickHouse will reserve, I mean, it will calculate and it will say, I'm going to mutate 3 parts, so I need more or less the size of 3 parts, even probably a little bit less if it's the lead, but it will calculate. And then it will begin reading the parts and it will begin applying the mutation operations in this case. So yeah, it's reading the parts, but this is concurrent and it's thread oriented. So other queries could read these parts because these parts are being mutated and still they are live, but the mutation didn't finish, right? So yeah, you can read it. I mean, you're fairly limited by the ER operations of your disk because you can read the parts concurrently, even if they are being mutated. They are not blocked because they are live. And when the mutation finish, this is where the interesting things come. When the mutation finishes, there's a new part. So what ClickHouse does is, okay, these 3 parts, original from the mutation, they are outdated. I'm going to mark them as inactive, and the new part will be active. So now queries will be reading the new part, not the old part. And what happens with queries that were reading the old parts? They will keep reading the old parts until the query finishes, and the next query will read the new part. So that's how it is. And there is another one about what does leader meaning in system replicas. This is a good one. Yeah. I would say like the leader replica, it's all about the pointer. I mean, there is a pointer in system replicas, and imagine that one of the 3 replicas, for example, it's always executed more operations in the write ahead log than other replicas. So this replica will be considered, let's say, as leader. It's like a run. But maybe another replica will write down more operations and it will be leader because it's ahead in time from other replicas. So this is what leader means. But basically, this is something interesting in older versions of ClickHouse. Right now, to troubleshoot and to do many stuff, we don't really see, we don't really check if it's leader or not. This could be something like a legacy, I would say. But yeah, this is what it means being a leader.
Great. Thank you. Okay, let's look at our last problem. And this is a quick one, 2 slides. It's lost replicas. So what is a lost replica? Well, for this, we have a lot of text, but let me cut to the chase about what a lost replica is. So when ClickHouse replicates, as we've already discussed, Keeper basically it keeps a log of the things that need to be replicated from the table. But that queue, if you will, has a limited length. So by default, it's 1,000 operations per table. So if a table goes offline, for example, for maintenance, it's the cluster is shut down. What will happen is it will basically come back and it has missed some things because the log has moved on and it's missed some things that it needed to replicate. In this particular case, ClickHouse, it's not a problem because what ClickHouse will do is it'll recognize, hey, I'm out of sync with the log. I'm basically lost. Now what I need to do is I need to go poll the you know the other servers and find out which parts they have and catch myself up. So it will basically go through a process of syncing itself with the parts on the other servers. Generally speaking, this just happens automatically and you don't have to do anything. But there are cases where your replica is for some reason so far out of sync that it doesn't work, or you may have cases where the replica itself, that was offline, has data that it really should share with other replicas. In that case, we're going to have to go through a procedure to properly sync the metadata with Zookeeper. Let's show how to do this. So what this does is it basically takes advantage of an operation called drop replica and another one called restore replica. So in this particular case, the first thing you do is you'll detach the table. And this procedure looks complicated, but it works like a charm. We use it fairly often to fix problems in production systems. You detach the table so that the table becomes unavailable. Uh, you then run this drop replica command, and what this does is it wipes out uh, the the node in Zookeeper or Keeper that's storing your metadata. So then what you can do is attach the table. It will come back, but it won't have Zookeeper metadata, so it'll be read only. And then what you're going to do is you're going to say restore replica. And what that does is internally it goes through a process of detaching all the partitions for the table and reattaching them. And as this happens, it will recreate metadata in Zookeeper. And then if you want to make sure that the replica is synchronized properly, you then run system sync replica to and that will basically wait until the replica is properly synchronized. One caveat on this procedure is you want to think a little bit before you use it. If you had uh, parts that were detached for a valid reason, this procedure will reattach them again. Uh, as it's running. So you want to think a little bit. Hey, do I have detached parts for some health reason or because of some maintenance procedure? In that case, don't run this. But this is the procedure. You run it. Basically, at that point, your replica should have the metadata correctly synced and should run fine. With that, looks like we don't have further questions on these. So let's go to the wrap up. We're pretty much at time.
I
Oh,
think we have one, yeah,
go for it. Yeah.
about project. I mean, it's not well, it's related and not related. It's about projections, but basically, it's um, sorry, I just lost it or not. Where is this? Yeah, about the efficiency of queries. Is there a way to tell ClickHouse which projection to use to execute a query? There are several of them from different types of queries. Yeah, well, I mean, yeah, short answer is yes. I mean, in newer versions, I'm going to write that down to you so you can check. If you have like multiple projections for a table, you can specify setting like a preferred optimized projection name, and you just equals to your projection name, and you are signaling Zookeeper or sorry, ClickHouse to use a projection, but let's say that it's up to ClickHouse to use it or not. I mean, most probably it will be used, but if because of the analyzer, if this preferred projection might not be used if it won't improve query performance. This is how it will work. Okay, but yeah, you can if you have multiple projections, it's like interesting to do that. Yeah. And another
Um,
one,
yeah.
there is another one about system restore replica, but maybe we can wrap up
Let's go ahead and
and
wrap up. And yeah,
okay,
if you answer that one background, because we're running over time here.
okay.
Uh, yeah, folks, thank you so much for your attention on this. Let's just wrap up and provide a few, just a summary. So very quickly, ClickHouse is actually kind of hard to break. Hardest part about this about doing a talk like this is actually simulating some of these conditions because they are tricky to recreate. So if you're running on a laptop or a test environment, chances are you won't see these problems. Where you will see them is if you have a production system with a lot of data and heavy load, then these are the types of problems that are going to come up. And those are precisely where the systems that you care most about. So you can fix these as we've shown, and we do this a lot. This is, I think Diego probably has more experience than almost anybody on the team in fixing things like broken parts. But really the best thing to do is to prevent the problems in the first place. So tune your square, you just write a good application. So use good schema with good compression levels so that you minimize IO and access data efficiently. Write efficient queries so that you read the least amount of data you need to. These will all help you help those queries run faster and put less load on the system. Second thing is adequate hardware. Just provision this to your systems so that when they need CPU, they've actually got it. That's the thing we tend to run out of, but of course, RAM is another one, and then storage bandwidth, things like that. These are all things that can that can cause ClickHouse to become overloaded and hence go from serving up a query say in 100 milliseconds to 15 seconds. Just lack of resources. Final thing is mutations and replication are great, but you don't want to abuse them. So having a big table and refreshing the entire contents of that table on a daily basis is going to be trouble because it's going to create a huge mutation which can block other operations from happening. As we've seen, it can also block replication. So these are and of course and then if you have a system crash during that period, then you've got a bit of a mess. So prevention is the best cure. Second thing, if these problems come up, the first thing you do, for example, replication, just wait. Sometimes they cure themselves because it's just load on the system. If it's a transient, as soon as it's passed, ClickHouse will bounce back. And then the last resort is wait in and fix it, as we've shown you here. The good news is, for the most part, these problems don't cause data to be lost, but there's definitely some careful analysis that goes into fixing some of them. We're available for help. If I mean, this is what we do for a business. Contact us and we can help you. There's another thing you could do is we do offer education in exactly this topic. In fact, some of the slides here are taken for our admin training class. So if you're interested in this and want to become an expert, we have a class starting on December 3rd. Invite you to sign up. Uh, it's quite popular. And and then here's some data sources. The Altinity knowledge base is probably the best place to find these specific uh, procedures. We tend to document these for our own sanity, but there are other locations. I will say I've listed the ClickHouse docs last, not because I dislike them, they're great, but these are problems that are not super, covered super well in there. Sometimes you're better off just going and reading the code, particularly problems related to settings. So with that, we are at the end of our topic. Our talk. We've run a little bit over. Thank you for your patience. I hope this has been good. If you have further questions, please come visit us on Slack and ask the questions. We'd love to. There is an Altinity Slack. I've got the link here. You can go to the altinity.com webpage. You'll see a little Slack icon. Join up. You can talk to us there, or you can contact us. There's also a link for that if you'd like to talk about specific things. So Diego, with this, I know we've got some questions out here, but I think we'll go ahead and because we're over time, stop. And for the folks who've asked questions, if you didn't get one answered, please do come contact. We'd love to talk to you about it. We do this for a living and love working with ClickHouse. So Diego, thanks again. Really appreciate your help on this. And
thank you, Robert. Yeah.
and one more time, huge shout out to uh, uh, to the entire support team for helping us prepare these materials.
Yeah, and for those questions, please go to Altinity TV Slack, and we'll be happy to answer that.
Yep.
We usually do. So
Yeah.
yeah, and that's for free.
Yeah. Thank you. And see you all soon. Thanks again and have a great day.
Bye bye.